everyone, my name is Alauddin and today I'll present my project on dynamic TSP for real-time warehouse operations. This project focuses on optimizing order picking routes in warehouses using Excel macros and Opensolver. So in warehouses, as we all know that order picking is a very crucial part, but traditional methods don't update when new orders arrive. This wastes time and increases cost. So my project solves this by using a dynamic model that updates routes in real time. The problem is that traditional TSP models are static. They don't change routes when new orders come in. This means more walking for workers and higher costs. So my goal is to create a model that updates routes automatically. And these are some of the objectives of my project, which include build a dynamic model that updates when orders change, use Opensolver to optimize routes, automate the updates or updated routes with Excel macros, and finally compare dynamic TSP with traditional methods like S-shape and return policies. And this is how I executed my project. First, I created a warehouse layout as a graph with pick locations as nodes. And on the right side, you can see the layout of the warehouse. The layout consists of multiple aisles, each divided into bins. The warehouse is organized with shared entry points between specific aisle groups such as B, C, T, E, F, G, and so on. The goal was to optimize the picking route by treating the layout as a graph where each bin is a node and each path between bins is an edge. We then calculated the distance between bins using the Euclidean formula, considering both horizontal and vertical movements. So for example, when moving from aisle B to C, we accounted for the shared entry gap of 4 units. Similarly, the distance between the vertical bins is of 1 unit. So this way the model accurately reflects the real warehouse structure and provides optimal routes. Now if we talk about the results, so the dynamic TSP model showed better performance than both traditional methods. It saved time by adjusting routes when orders changed. In comparison, S-shape and return policies were less flexible, especially with frequent orders change. So in conclusion, we can say that the dynamic TSP model improved warehouse efficiency by reducing walking distance and adjusting routes in real time. This leads to faster order picking and cost savings, and in the future this model can be further enhanced by integrating it with warehouse management systems. Now I will show you my Excel work for this project. I have organized everything into different sheets to make it easy to understand. So here is the first sheet, node coordinates sheet. Here I have all the bins listed with their X and Y coordinates. These coordinates help calculate the distance between bins using the Euclidean formula. Next is the distance matrix sheet. It shows the distance between every pair of bins which we calculated using the Euclidean formula and the coordinates from previous sheet. This helps the model calculates the shortest route for picking. Next is the TSP model sheet. It has all the 324 bins and their distances. I used Opensolver to find the shortest route if the picker has to visit every bin. The result here shows the optimal distance for this complete route, which is 327.236. And here we have the pick list sheet. This sheet shows the current orders that the picker needs to follow. So for example, if we come to this sheet and click on the update orders macro, it will automatically update all the orders from pick list. And now if you click on this solve TSP macro, which will solve our Opensolver model, we will get our objective value, which is 44.40, and using the summary macro we can see that the total distance covered was 44.40. But here is the point. Regarding our pick list sheet, I have linked it with the CSV file which is on my system, so the orders are updated automatically when I load that file. and I have used a macro to make this quick and easy, which I will show you in the next sheet. So this sheet has all the macros. There are buttons like clear orders, which will clear all the previous orders, and this import new orders from CSV file macro will import all the orders from our CSV file, which we can see here. And now we just have to click on update orders, and it will get updated automatically. And again, we would just have to click on the solve TSP macro to find our objective value, which is 29.85. Next is our S-shape policy sheet. This sheet shows the S-shape picking policy. The macro here finds the best route by moving in S pattern through the aisles, and it's good when the picks are spread out evenly. So for this I also have created a macro, and using that macro you can easily calculate the total distance, which is 77.98. And in this sheet I have done some manual calculation for S-shape policy to make sure that the macro works correctly. And as you can see, both results match, which shows that the macro is working fine. This is the return policy sheet. The picker enters and exits the aisle from the same end. This method works well when picks are mostly at one end. The macro shows the best route and calculates the distance, which is 155 units. So now let's compare the performance of our three picking policies: dynamic TSP, S-shape, and return policies. As you can see from the chart, the dynamic TSP method is the most efficient, covering a distance of just 29.85. The S-shape policy comes next with the distance of 77.98, and the return policy has the highest distance of 155. So this clearly shows that using a dynamic approach significantly reduces the pick distance compared to traditional methods. Thank you so much for your listening.